Hello, retro enthusiasts, and welcome to another episode of Retro Computers and Electronics Workshop. Today is the second part of Sprites and Sound on the Commodore 64. We are going to learn about the binary system and the hexadecimal system. As humans, we use the decimal system, which is based on 10 different digits, 10 different symbols, maybe because we have 10 fingers in our hands, and we can represent any number with that. We can also represent any number in binary, but in binary we use only two symbols, 0 and 1, and that's what computers use. We will also learn the hexadecimal system and why it is important to know about it. The Commodore 64 is a much simpler, as a way of saying, computer compared to nowadays computers. So when we want to accomplish a particular effect, graphics, or programming something fast like in a video game, we will need to learn about machine language. To understand how that works, understanding also the binary system, the hexadecimal system, is very important. It might sound a little bit difficult or complicated, but trust me, it's very, very simple. And we don't need to go really deep into this. We just need to know actually what it's about and how to convert, but mostly about its nature, what it's about. So let's get into it. Well, here we are. Let's see. So the decimal system, as I was saying before, is based on 10 symbols, basically from 0 to 9. With these symbols, we can represent any number that we want. For example, let's say the number 410. We can also get this number by doing this simple operation. 4 per 100 plus 1 per 10 plus 0 per 1. That would be 400 plus 10 plus 0 equal 410. Maybe this is not the best number as an example, but the thing is that, as you see, the 4 is multiplied for 100. The 1 is multiplied by 10 and 1 for 0. So if you remember in high school about powers and exponentiation, you have that, for example, 2 to the power of 2 is equal to 2 per 2 equal to 4. And 2 to the power of 1 is equal to 2. And that 2 to the power of 0 is equal to 1. So what's happening here is that we have powers of 10. So basically we have that the first position will be to the power of 10 to 0, the power of 0. The second position will be 10 to the power of 1. The third, 10 to the power of 2. So as you can see, first position, second position, and third position will be the different powers in order. So basically that was how we know which number we have to multiply based on their position to get the actual value that we want. Okay, so let's see this in a little table. Maybe it's easier. Excuse the fact that the cells are not on the equal width, but it's okay. So here we can see that at every single position, we have a corresponding power of 10, representing each position. So in the case of 4, power of 10 to the second power is 100, then 10 and 1. Okay, so in this way we can calculate any, that's how we calculate any decimal number, any number basically. So what happens in binary? In binary, we use only 0 and 1 to represent any number. So for the computer this is useful, and the reason it is useful is because 0 is like switch off, 1 is switch on, basically no electricity, and 1 is electricity, so on off. And it's a very simple way of determine that state on an electronic circuit. So for the computer it's easier to understand a 0 and a 1 than having 10 values. We will need basically almost 10 different levels of voltage in an electronic system to actually determine, forget it. The problem is that binary is very impractical because, I mean, you can represent any number with it, but any single number would be huge to represent in binary. So for us, for humans, it's way easier to use a decimal system. But for computers, it's way easier to use the binary one. So to convert this binary number into a decimal one, let's use a similar table that we used before. In this table, as the table before, we can see that at every single position, we have a power of 2. So if we calculate the power, then we have 1, 2, 4, 8, 16, 32, 64, 128. This is basically 2 per 2 ones, 2 per 2, then 2 per 2 per 2, 2 per 2 per 2. I mean, you remember the exponentiation, how it works. Basically, then, I mean, if you don't remember that, it's very simple. This is the base, this is the exponent. So you have to basically multiply the base as many times as the exponent says. If it's 2, then you have to do 2 per 2. If it says here, for example, it's 4, then it's 2 per 2 per 2 per 2. Let's try with a random binary number. So to calculate this is very simple. What we have to do is just check the position here. So it will be 16 per 1, then plus 8 per 0, which is the position, plus 4 per 1, this position, plus then 2 per 1, which is this position here, plus 1 per 0, which is this position here. So we have 16 plus 8 plus 4 plus 2 plus 1. And if we add all these together, we are going to get the wrong number because I made a mistake here. Actually, 8 per 0 is 0. And 1 per 0 is 0. And it is 22. So as you can see here, there is something interesting. We have 8 positions here. And why did I choose 8 and not 9 or something like that? Because every single digit of a binary number, in this case, for example, this one, each of these digits is called a bit. And a bit can be 0 or 1. And that's where the 8-bit computer name comes from, basically. Because what it means is that in every memory position, every memory cell of this computer, the maximum value that can be stored is an 8-bit number. And an 8-bit number means a binary number composed of 8 bits, of 8 binary digits. So 8 ones and zeros, basically. If we add all the numbers here in the position from 128 to 1, we will get 255. So it means that you can represent numbers from 0 to 255. That's 256 numbers. So you might think how the computer can represent a bigger number like 1,000 or 10,000, a million. Well, there are different techniques to accomplish this, but we are not going to see that now. The important thing here is that you see how to convert a binary number into a decimal one. Now let's take a look about the hexadecimal number. This is a number based on 16 symbols, basically on 16 different digits. So in order to accomplish this, well, we have the same from 0 to 9. But then we also have to add the remaining ones to reach 15 because it's starting from 0, so not 16. So where are we going to do? Well, instead of creating new symbols or something like that, what we do instead is using the letters of the alphabet. So basically in hexadecimal, the letter A, which is not a letter, it would be the number A, is 10 because that's the one you have after 9. So what happens when you reach F? That would be 15. Well, basically the same as you do in decimal system. When you reach 9, then you go back, you take the 1 and you put it with a 0 and you got 10. Well, here is basically the same. When you reach F, and that would be 15, and you want to represent 16, then you put 1 and 0, the same as you did before, because it's basically you recombine these digits, these symbols, in a way to represent a number. But because we are already using 2, it means that it's a positional system as we use in decimal, as we use in binary. And this positional system, you guess it, is going to be powers of 16. So it's going to be to the power of 0, 1, 2, and so forth. If we make a simple table like we did before, maybe it's easier to understand. For example, the number A2. So following the same procedure, same rules we followed before, this would be A was 10, so it would be 10 per 16 plus 2 per 1. And this would be 162. So A2 is 162 in hexadecimal. So I want you to notice something here. Why do we use hexadecimal if the computer is using binary? So who cares, right? Well, the reason is because, as you can see, look at here in the position, you see that actually the different position is on multiples of 2, meaning that hexadecimal is kind of between our decimal system and a binary system. It's a way to basically make it easier also for us to understand binary values that exist on the computer. For example, in hexadecimal, the number f is equal to 16. But in binary, 16 is 1, 1, 1, and 1. So you see that f is the full, basically all ones turned on. Well, that's 4 bits because there are 4 ones, right? So what if we have 2f, f, f? That would be 2 sets of 4 bits, basically 8 bits. So that would be 1, 1, 1, 1, and 1, 1, 1, 1. And that's 8 bits. That's a full byte, full on ones. And that's 255. So basically, you have here in hexadecimal, you see that every 2 digits, every number of 2 digits in hexadecimal is equivalent to 1 byte, to 8 bits. And maybe I didn't mention before, but 8 bits is 1 byte. Is that the definition of it? So when you hear about 1 byte, it's basically a value made up of 8 bits, of 8 binary digits. So here, FF, you can see there is directly, you have a direct idea that FF is basically a byte full of ones. So you can play with this a little bit. For example, let's say if I have multiples of 2, right? So I have like 1F. What would be in binary 1F? So we know in binary 1 would be 1, but then the F is for bits of 1. So 1, 1, 1, 1. So that's how it would look like. See how fast it is to represent these in binary. In decimal, this number would be 31. So it's like, okay, what? So I mean, it doesn't really have any particular value, but in binary, you see that there, basically you can connect a different binary pattern of different combinations of 1 and zeros to an hexadecimal number way easier than you can do that in decimal. And that's the usefulness of using hexadecimal. So the important thing here where I want to get is about the memory. So imagine the Commodore 64 memory, the 64 kilobytes is like 64,000 cells, which in each of them you can put an 8-bit number. So if you get this idea of the memory, let's imagine it as an array of different boxes, for example. So here we see that, okay, we have this memory. Imagine in your head that is like something like that. So if I have in this position here the number 42, for example, and in this one the number 7, well, how do I get to that number? How do I know that? Well, because the memory has a memory address. So you can pinpoint every single memory cell by its address. So let's say if we label this imaginary memory here like these. So each different box has an address. So you can say, okay, in the memory cell number 4 here, I have the number 42. Or I can say, okay, put the number 30, for example, into the memory cell 5, and or change it, replace it, and whatever. So the thing is that inside the computer, inside the Commodore 64, you have different memory locations which have a particular kind of effect. For example, you can change the background color. Where the background color is controlled, well, because there is a particular memory address which has the value that represents the color of the background. So if you go there and you change that value, you change the background of the screen, or you can change the character set, and you can do a lot of things with this. That's why it's important to understand this kind of this relationship between the value that you can, the 8-bit values, the maximum values you can put in every memory cell, every memory location. Let's take a look at an example on the simulator, so maybe it will make things a little bit easier to understand. Okay, we are back here in our emulator, and let's type, for example, a poke command. What is a poke command? It's a command called poke, but it basically changes a memory address with the value that you want. So you put the memory address first. In this case, this is the memory address of this internal, the blue background that we see here. And the second value of this command is the color. The Commodore 64 has 16 colors, so here you can choose any of them. Let's put, for example, a black background, so that will be 0. If I type enter, you see, it changed to 0 because the computer is reading in that memory location. The 53281 is reading in that location the color of the screen. So every time it's refreshing that, checks that location, say, okay, this is the number, that's the color, I'm gonna show this color. So for example, let's say we want to change the border to also let's make it black, for example. So the command will be the same, poke, but in this case we had to change the memory location. And that is very close to the other one, is 53280. So now we change it into black everything. So this is a way to show you basically what is going on here. If I keep changing, for example, let's say poke 53280 into 1, that is white. And in the Commodore 64, if you go up with the arrow keys and you go back to the line that you typed before, if you change something, for example 2, that would be red. If I type return in that very line, it's going to execute any command that the cursor is in. So be careful, sometimes if you move around with your arrow keys and you end up somewhere where you have a command or a value and by mistake you press return because you just want to move the cursor down, it's going to actually execute that command. So just be careful with that. So if we type enter here, you see we change into red. And then we can go all the way to all the different colors that we have available for the Commodore 64, which are only 16, but at that time that was huge. And this concludes our episode about the binary and hexadecimal system. In the next episode, we're going to talk about the screen memory map, basically how to position a character, any character that we want, in any position on the screen. This is important because we are going to cover different things, like for example the PES key, which is PES key is a codification used by Commodore for representing the characters and where to find this information and the different codings that are used for that. With that, we can create simple programs, for example, moving a character from the PES key table around the screen, for example, by using your arrow keys or any Commodore joystick, for example. But we are going to try to avoid the joystick so far until we get more advanced, because most people are going to use probably the emulator here. The emulator can support the joystick too, but let's try to keep things simple for the moment. So in the next one, we are going to really get more into our Commodore 64, into programming it. No more theory. We already know how our development environment. We went a little bit with the theory about binary and hexadecimal systems. And next time we are going to just work directly on the computer, program a little bit. And in the process, we're going to learn the basic programming language, which is this is not the focus of this series of videos to learn basic programming language, but is going to be easy to learn it by doing. That's the way basically I learned it when I was a kid and I have my computer, and I think it's an easy way to learn something new by just having fun doing it. If you enjoyed this video, please give me a thumbs up and subscribe. You know the final for every YouTube video, please thumbs up and subscribe. And also you can help me supporting on Patreon. In that way I can create more of these videos on a more regular basis. Simple, small contribution is enough, is a big help. So if you like it, consider checking on Patreon too and become a Patreon supporter. Also on Patreon I will post more content that is on the YouTube channel that you cannot find online, only for patrons. Thank you and see you next time.